I would like to thank the university for the invitation to give this inaugural lecture. It is certainly unfortunate that this event cannot take place in person and that we have to do without the social aspect. I'm therefore even more grateful for the people who came today to hear a bit about how category theory can help us in physics. And I promise I will keep things simple. I have to start with a disclaimer. This talk will only give a flavor of how category theory is related to quantum field theory and beyond. Some statements are exaggerated to simplify the presentation. This is not a scientifically rigorous talk, but I hope you will enjoy it, whatever your background. Also, please do not worry about the involved mathematics. Compared with life, it's easy. Many creation myths start or involve light emerging from darkness, and this is also the starting point of our story today. Michael Faraday was an English scientist in the 19th century, and he is probably one of the most underrated scientists in history. In 1845, he announced, "I happen to have discovered a direct relation between magnetism and light, also electricity and light, and the field it opens is so large and I think rich." In particular, Faraday discovered that light was nothing but an electromagnetic wave. The complete theoretical description of electromagnetism was then given by Edinburgh's very own James Clerk Maxwell in 1861, building on the work of many other scientists before him. The relevant field equations are called Maxwell's equations, and they form one of the oldest cornerstones of my research area of mathematical physics. The precise form of the equations displayed here is irrelevant to our story. We merely note that there are quite a few complicated looking equations, and while they look like there's some kind of order in them, it's not particularly easy to spot it. A decisive ordering principle in modern theoretical physics is symmetry. Symmetry tells us that things are invariant under particular transformations. A perfect ball, for example, looks the same no matter how we rotate it in space. Similarly, we would expect that the general physical laws do not depend on the rotation of our laboratory. For example, we should measure the same effects anywhere on Earth, whether we are in Scotland, Germany, or in Australia. Such laws that are invariant under spatial rotations are best written in terms of vectors. These are mathematical quantities that have both a magnitude and a spatial direction. It was Oliver Heaviside who insisted on using vectors in electromagnetism to exhibit the spatial symmetry of Maxwell's equations. He announced, "And it is a noteworthy fact that ignorant men have long been in advance of the learned about vectors. Ignorant people like Faraday naturally think in vectors." This was clearly meant as a compliment to Faraday, who had not received much of a formal education. Oliver Heaviside's reformulation of Maxwell's equations is already much more concise, as we see here. We can also see a certain amount of repetition in the equations themselves. Again, the explicit form of the equations is relevant for our purposes, but you see the electric and magnetic fields E and B appear as vectors. We say that this formulation makes a spatial symmetry of the equations manifest. The symmetry is evident from the form of the equations. Heaviside saw that in special cases, these equations exhibit some form of symmetry under the exchange of E and B. Unfortunately, he missed that Maxwell's equations possess, in fact, a much larger symmetry. Most of you will know that in modern physics, space and time are not separate entities, but they belong together in what we now call space-time or Minkowski space. This is one of the cornerstones of Einstein's special theory of relativity. In 1908, Hermann Minkowski proclaimed, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." To make space-time or Lorentz symmetry manifest, we have to work a bit harder and switch from vectors to more general objects in the description of Maxwell's equations. Here is again Heaviside's reformulation of Maxwell's equations. We can now package the electric and the magnetic field in a table or matrix F. The other objects in the equations, the charge density ρ and the current density J are packaged into a vector in Minkowski spacetime. Mathematically, the table is what we call a differential 2 form, and the vector is a differential 1 form. We can then write Maxwell's equations in this ultra-compact form, which makes all their symmetries immediate. Maxwell's equations in terms of differential forms contain the operator d, which is called a differential. This is a linear map that takes generalized vectors to generalized vectors. Its characteristic property is that it produces 0 when applied twice to a generalized vector. This is an algebraic shadow of the geometric property that a boundary has no boundary. For example, the boundary of a disk is a circle, but the circle itself does not have a boundary. A differential does not seem particularly interesting by itself. Its applications and implications, however, are vast. They are studied in the rather young mathematical field of homological algebra. Henri Cartan, a crucial figure in 20th century mathematics, was aware of many of these consequences and expressed the wish to only understand the beautiful consequences falling from the concise proposition d squared equals 0. If we work on Minkowski space, we have the so-called Poincaré lemma at our disposal. Recall that half of Maxwell's equations are encoded in the relation df equals 0 in the language of differential forms. Poincaré's lemma then amounts to the fact that there is a one form or vector A, and the electric magnetic field strength F is the differential applied to A. This A is called the electromagnetic potential, and it brings geometric meaning to Maxwell's equations, connecting them to principal fiber bundles. Here we merely focus on what is called the gauge symmetry of Maxwell's equations. Because D applied twice is 0, there's a redundancy in the electromagnetic potential. Both A and A plus D of alpha, where alpha is an arbitrary function on Minkowski space, yield the same field strengths, and measurements cannot distinguish between both. This redundancy can be interpreted as an equivalence of the field configurations A and A plus D alpha. It can also be seen as a symmetry of Maxwell's equations under the transformations A goes to A plus D of alpha. We have spent quite a bit of time now on the theory of light, and most of this is over 100 years old. But I think we can learn some important lessons from these historical developments. Namely, it is good and useful to do the following. Firstly, look for unifying descriptions, as Faraday did, combining light with electricity and magnetism. Secondly, extract the essence of our object of study, as Heaviside did when introducing vectors. Thirdly, look for symmetries, as the spacetime symmetry of Minkowski or the gauge symmetry of Maxwell's equations. Fourth, identify physical equivalences. One may add a fifth one, occasionally doubt or revolt against the learned people in your research area, as Heaviside did with insisting on using vectors. Remembering Eugene Wigner's observation about the unreasonable effectiveness of mathematics in natural sciences, we may wonder if the above aims can somehow best be achieved by using modern mathematics. And indeed, there's a meta-mathematical framework that does precisely this. Enter category theory. Category theory was born in the 1940s, arising from work of Samuel Eilenberg and Saunders MacLean in algebraic topology, but it certainly has earlier ancestors. Category theory is best described as a general mathematical theory of structures and the structures of structures. To explain category theory, let me give you an operational simple example. Let's cook some pasta. We have a couple of states that our kitchen can be in, and a number of operations that we can perform to get us from one state to another one. For example, we can take an empty pot and add water to this pot to get a pot with cold water. If we bring it to a boil, add pasta and keep boiling the pot, we end up with cooked pasta. Note that an operation may be invertible. For example, if we have a pot of boiling water, we can turn off the stove and wait to get back to a pot with cold water. On the other hand, it is not possible, at least not with the technology used here, to get cooked pasta back into this uncooked form. At each point, we can also simply do nothing and we stay in the same state. Also, we can always combine or concatenate arrows to get a longer arrow between two states and I haven't depicted either of them here. This, in short, is a category. The states are mathematical objects, and the arrows are transformations or morphisms of one object to another one. Experience has shown that, not unlike space and time, mathematical objects should be studied together with their transformations. We thus package them up into a category. The above example perhaps doesn't seem particularly impressive, but it opens up our mathematical thinking. Without categories, we were thinking mostly in a static way. Two objects can be equal, as for example x can be equal to 5, or they can be different, as for example 7 is not equal to 5. With category theory, however, we can express more dynamic things. Two objects can be equal, or equivalent, that is related by arrows in a particular way, or related by arrows in another way, or unrelated. Having liberated objects from the shackles of strict equality, we notice that the arrows are still limited. So we simply repeat our trick and introduce arrows between arrows, leading to what is called a two-category. Interestingly, categories themselves form a two-category, and it is the arrows between arrows of this two-category that Eilenberg and MacLean set out to study originally. In this framework, we also have a good notion of equivalence. For two categories C and D to be equivalent, we require two arrows between these, phi and psi, such there are compositions between them and they are not strictly equal to the identity on the categories, but related by an arrow between arrows to the identity. Having introduced arrows between arrows, we can ask with Shakespeare's Rosalind, why then can one desire too much of a good thing? So we introduce arrows between arrows between arrows, and so on ad infinitum. The result is what we call an infinity category. Looking at all these diagrams, Steve Avode, a mathematician and philosopher, came up with a better name for category theory, namely archery. So why do I insist on using category theory? What are the benefits? Well, I find myself often in a situation where I need to generalize familiar mathematical concepts from particle physics in order to describe something that arises in string theory. Category theory makes this easy because as a mathematical framework, it allows you to reason abstractly about mathematical structures. It often tells you what mathematical structures ought to exist. John Baez summarized this nicely with, category theory is a subject where you leave the definitions as exercises. Categorical reasoning can also tell you what properties the objects you define should have. These type of arguments are factually known as abstract nonsense. For example, you would say that a statement is not specific to a context, but it follows simply from general abstract nonsense. Let me give a brief example generalizing Maxwell's equations. Half of Maxwell's equations just state that they describe a gauge theory. Geometrically and from a category theory perspective, a gauge theory can simply be described as a functor from the path category to the category BU1. In plain English, this just means that we consider paths in our Minkowski spacetime and associate to each path an angle. We do this such that if we concatenate two paths, then the angle associated to the new path is the sum of the angles of the individual paths. This is now a particle picture, as particles follow paths in spacetime. A string, on the other hand, would sweep out a surface in spacetime. Thus, a higher gauge theory is an assignment of angles to surfaces in such a way that angles add when the surfaces are joined together. Category theory then tells us that there are gauge equivalences in these theories and what precisely they are. They all follow from abstract nonsense. Another example of an application of category theory takes us into the exciting world of cutting-edge particle physics. We can use category theory to argue about scattering amplitudes, the things that people measure at the Large Hadron Collider. You see here a picture of the Large Hadron Collider at CERN, where, for example, the Higgs particle was discovered in 2012. In this 27-kilometer long tunnel, in a depth between 50 and 175 meters, protons are accelerated so fast that they are only 3 meters per second slower than light. Once they reach this speed, they are made to collide. The results of the collisions are then measured at the detectors, For example, the CMS detector on the left of the picture or the Atlas detector on the half right. These detectors are quite impressive, both in their size and in their complexity. On the left, you can see people standing in front of the CMS detector. On the right, you see the schematics of the almost twice as big Atlas detector. The pipe in the center is where the particle beams are guided through, and the beams are crossed in the center of the detectors. The detectors then catch the particles produced in the collisions and measure their properties, which are then compared to theoretical predictions. These theoretical predictions are now produced from what we call perturbative quantum field theory. We model the situation by considering a bunch of free incoming particles, the proton beams at the LHC. These then enter an interaction region, namely the centers of the detectors at the LHC, where the beams are crossed. This produces a bunch of free outgoing particles, which we measure inside the detectors. A perturbative quantum field theory now mainly gives us two things. Firstly, it gives us a propagator, or probability for a particle to move from A to B. Secondly, it specifies interaction vertices, probabilities for a particle to split into other particles or to be produced from combining other particles. We usually depict these as lines and vertices so that a complete interaction process becomes a mathematical graph. Quantum particles are now strange in that they do everything that they are allowed to do, and they do all of this at once. Each allowed interaction process contributes to the outcome with a probability assigned to it by the quantum field theory. So what we have to do is to fill in the interaction region with all possible graphs of Feynman diagrams and sum over all of them. The result is a scattering amplitude, which describes the probability of a particular scattering outcome to occur. Now, the surprising thing is that something very similar happens in higher category theory. Infinitesimal symmetries are commonly described using Lie algebras in mathematics. One can generalize these Lie algebras to infinity categories or, equivalently, to what are called L-infinity algebras. And these can describe higher infinitesimal symmetries, but for our purposes, this plays a secondary role. An L-infinity algebra is simply a vector space, together with a differential, and further maps that take an arbitrary amount of vectors as input and produce a vector from them. Moreover, each L-infinity algebra comes with an equivalent simpler form called minimal model. Minimal models are now computed by the so-called homological perturbation lemma. This is one of the many rich consequences of the concise proposition d squared equals 0 that Cartan alluded to in his quote that we encountered previously. Explicitly, we take elements of the minimal model, embed them into the original L-infinity algebra, and sum over all possible ways of combining them by vertices. We then project the result back to the minimal model. In other words, computing the minimal model of an L-infinity algebra is precisely the same thing as computing a scattering amplitude in a perturbative quantum field theory. When I first realized that this was true, I was shocked, both by how close the relation actually is, and that this statement is not contained in all mathematical books about quantum field theory. This observation actually extends to an equivalence between field theories and L-infinity algebras. This correspondence is very useful indeed. Firstly, it gives us a clean mathematical formulation of perturbative field theory, and we can explain the principles of perturbative quantum field theory to any mathematician, in particular algebraist. Secondly, the homological perturbation lemma implies a recursion relation, and we can use this recursion relation to compute and prove things about scattering amplitudes in quantum field theory. Thirdly, it allows us to reason more abstractly about field theories. For example, it shows that any field theory can be reformulated as a field theory with purely cubic interactions. This is a consequence of the stratification theorem of homotopy algebras. Finally, it suggests that any further structures hidden in scattering amplitudes, and physicists suspect that there are quite a few, must be homotopy algebraic refinements of L-infinity algebras. My group have been using all of the above in our research. Let me give you a concrete important example that my group is working on at the moment, and this is called the double copy. For this, I need to introduce two particles or fields, the gluon, which literally glues together smaller particles called quarks to protons and neutrons. Gluons are vectors in a double sense. They have a direction both in space-time as well as an internal or color space. Their dynamics are governed by a gauge theory known as Yang-Mills theory, which is a generalization of Maxwell's equations, and this theory is reasonably well understood. On the other hand, we have the gravitons, which are responsible for keeping you in your chairs. They are also doubled vectors, but now with two directions in space-time. Their dynamics are governed by Einstein's general theory of relativity, and they are the particles mediating the gravitational force. From our previous discussion, we already know that we can reformulate gravity and Yang-Mills theory such that they only come with cubic interaction vertices. The double copy, however, refines the statement. We can do this such that the scattering amplitudes of these theories factorize in three factors, namely a color factor, a spacetime factor, and an interaction factor. Moreover, these factors are actually the same between both theories. In other words, if you know the scattering amplitudes of Yang-Mills theory and their factorization, you know the scattering amplitudes for gravity. Moreover, as my group showed, all this is best formulated using category theoretic tools or homotopy algebras. Now, all of this is great, but unfortunately it's not enough. Quantum gravity is actually very hard, because if you compute things, you have to find a way of interpreting infinitely many infinities. This is believed to be impossible even for a theoretical physicist. Therefore, quantum gravity, as currently done, has little to no predictive power. Yang-Mills theory does not suffer from this issue, and we can infer some properties of gravity from the double copy, but at least in its current formulation, the double copy is not good enough to get a full description of quantum gravity. Fortunately, however, there's a metaphysical framework helping us a bit further. This framework used to be called string theory. It starts from the simple idea that we should replace particles by strings or loops. Our Feynman diagrams from above get thickened to tubes, and this helps to tame the previously mentioned infinitely many infinities. But then it quickly gets complicated with all kinds of higher dimensional objects, known as branes, entering the picture. The original promise of string theory, which was still around when I started my PhD, was a unique and elegant theory of everything. That is, string theory was expected to develop into a unified description of all the physical fundamental forces. From what we have learned so far, a unification of our current physical models seems to exist within string theory, but it also allows for a huge number of possible universes, and it is unclear why in particular our universe should have been selected as the real one from all of these possibilities. As a consequence, again, string theory has, just as quantum gravity, little to no predictive power. This realization, together with envy of the generous funding and prestige in the 90s and early 2000s, led to a number of theoretical physicists voicing strong criticism of string theory. While some of their points are justified, I think that most of their critique is actually too short-sighted. To me, string theory is a coherent framework of ideas that allows us to think about quantum field theory, not unlike the way that category theory allows us to think about mathematics. Let me give an example, namely the double copy we saw previously. From a quantum field theoretical perspective, it is quite unclear why gluons and gravitons should have related scattering amplitudes. From a string theory perspective, however, this is reasonable to expect. A scattering process of strings can often be interpreted in two equivalent ways. One involves closed strings that describe gravitons. The other one involves open strings describing gluons. On the left, for example, we see a closed string being exchanged between two d-branes, moving upwards in time. On the right, we see two open strings forming spontaneously between two d-branes, moving horizontally in time and each sweeping out half a cylinder in space-time before they annihilate each other again. Since this is one and the same process, it gives rise to a relation between scattering amplitudes for gravitons and gluons at the low energies where strings appear as particles. Another example for the power of string theoretical thinking is the postulate of a completely new and mysterious quantum field theory, usually called the 2-0 theory. Exploring this theory has been at the heart of my research at Heriot-Watt University. Because of its fascinating properties, a full description of this theory has become a holy grail within the string theory community. Even though this theory was postulated to exist in 1995, we are still lacking a good understanding. The theory describes a particular form of strings in M5 branes that form the boundaries of M2 branes. This theory is crucial to our understanding of string and in particular M theory. It is, however, also very interesting from a field theoretic perspective, as it is also expected to be in some sense the most symmetric field theory in existence. There are strong arguments suggesting that it is a pure quantum theory, and it's generally believed that we cannot approach it using the Feynman diagrams I talked about before. Using tools from high category theory, however, my group found that at least a partial classical description can be made. In developing this description, we discovered fascinating new mathematical structures that should find applications outside of string theory. Okay, let me sum up. We have seen that historical experience provides us with some good practices to follow when studying the world around us. We should try to find the essence of our objects of study. We should try to unify things, and we should try to seek symmetry. This can be done with a meta-mathematical framework of ideas called category theory. In our research, my group applied this to the study of high gauge theories, scattering amplitudes, and the double copy. There's a second metaphysical framework of ideas called string theory that lets us reason abstractly about field theories. Not only does string theory suggest the double copy, but it also predicts a higher categorical treatment of the double copy as a truncation of the higher categorical structures within string theory. String theoretic reasoning also predicts the existence of the 2-0 theory, a fascinating and still mysterious field theory which has been at the heart of the research in my group. Mathematical physics is classified as applied mathematics, and some of the topics I presented look like they may have concrete applications. But this is not what drives me in my work, at least not most of the time. Donald Knuth said that science is what we understand well enough to explain to a computer. Art is everything else we do. Much of my research does indeed feel like doing art, exploring the immense order underlying the structures governing our universe and watching things fall neatly into place, for example in a category theoretic description, provides a very addictive aesthetic pleasure. Let me end with some brief thank yous. First of all, I would like to thank the various organizations that supported my research financially. Without their support, I would certainly not be here today. I would also like to thank my colleagues at Heriot-Watt from the department, the school, and across the whole university for creating a friendly atmosphere that was conducive to an ideal working environment. I certainly have to thank my current and former collaborators, with shared frustration and elation in our joint adventures in mathematical and theoretical physics. I would like to mention in particular Martin Wolf, who has also been a very good friend since the time of our joint PhD at the University of Hanover. I'm also very grateful to the current and former members in my research group. I often learned as much from them as they did from me. Without all these people, my research would mostly consist of staring at a sheet of paper instead of having the inspired discussions and intellectual adventures that I've had. Finally, I would also like to thank my family, my wife, Kirsty, my children, Katja and Elisa, and my parents, Helmut and Inge, and my brother, Florian, for their encouragement and for their emotional support over the years. When you're stuck chasing a minus sign in an hour-long, lengthy homotopy algebraic calculation, it is sometimes very useful to be reminded of the important things in life. Thank you very much for your attention.